So hopefully you got a lot of that done, but if there's anything you're stuck on, we're going to continue here. So the first thing was our Excel program. So these times, we want these to go down to 10 seconds. Okay, and our Euler's method. So we do equal to the next, which is in this cell B3, is equal to previous. So step size here, which is 0.1 times previous slope. Now the slope is the derivative, the minus lambda over m times v, but the lambda here we're saying was 1.5 and the m was 2, so it's minus 1.5 over 2 times v, and it should be the previous v, so we'll put in v there. And now this is where we have the smart thing. We don't have to drag it down. That was just get this thing, and then to insert our graph, go like this. There we go, job done. Right. And then there's the thing to check. So the 4.3, we'll just check it. Approximately 0.007. Good. That's probably say, so this isn't actually the velocity at time 4.3. This is our Euler method approximation to it. Now the goal seek. So this needs to go down to 1 second. Okay, and this Euler method now is good, just again with the smart thing. Okay, so what we want to do is we want to adjust this until this is 0.01. So this one, as it stands, is going to 0 too fast. We don't want it that small after a second. We want it to go to 0.01. So the what if analysis data, what if analysis goal seek, set cell 102, which is the final velocity, equal to 0.01 by changing the damping coefficient. Now this should be kind of instant. See, it's working through it and it's got the target value that we wanted, and it's changed the damping coefficient to this. So we should see the final velocity very, very close to 0.01. Yeah, it's just a difference in the, I guess, is that the 4th decimal place, something like that. So that's that done. Job done. The next one is our VBA here. So we've done the first bit of it. We've done all this. So now we're into the loop, I think. Yeah. So we want to write a loop, and we've set a lot of it up already. So this actually, as written, is wrong. I don't know why I wrote 2. It should be, okay, so this is row 2, column 1. This is going to print, so if we go through it, F8, that's the macro recorder, and it's given all these their initial values, and then in cells 2, 1, which is here, it's going to print the current value of t, which is 0. Okay, and then it's going to keep looping while the time is less than the final time, but it's just going to keep doing the same thing because the time is stuck at 0 and the final time is 10. So we'll just stop here. So really what we want is not to print constantly here, but to come down. So we want this row number to be variable, and that's our R. So that's going to print the T, and then we want to print the V in column 2. Okay, the next time, the time just ticks on, just adds a step size. The V just is Euler's method, so the next V is equal to the previous V plus the step size times the slope, and the slope is minus lambda over m times V, and this is pretty much the whole job. I just press F8. Idiot features here. This was the other thing. So obviously this is not doing what we want, and what happens is we go through it, the time is updating, but the R is fixed at 2, but of course we want that to go up every time, so we do R equal R plus 1. And there we go, that's what we want. We can insert a graph. There we go. Lovely job. And then I can say, so it's asking us to do the framework. Okay. Expect a few one-off errors. So for example, this should go out to a final time of 10. It's going to 9.95. This is not a big deal. If you want to find out what's going at 10, you can put in 11. That'll work. Or slightly cleaner is to do while time is less than the final time plus h. Now when this reaches 10, yeah, I guess this is actually working as we expect. Because when it reaches 10, so it'll go from say 9.9 to 10 here, or 9.95 to 10, it should stop. So this will work better. And remember, it went down to 11. Oh yeah, change it back. But we did the macro recorder. It's going to delete the previous run. Okay, so it's asking us to play with it a little bit. Put the initial velocity equal to 0.2. Okay. The mass equal to 2, and vary the damping coefficient from 0.5 up towards 10. So let's see what happens. Okay, here it's going to 0 quite quick. We make the damping stronger. It should go to 0 faster. Yeah. And say 2, it's slowing it down faster. Go up to 5, it's slowing it down faster. When we get to 10, it should really, that's really strong damping. It basically do really quickly. The other one, put the initial velocity equal to 0.2, the damping equal to 1.5, and adjust the mass. So 0.18, that's a very light thing. The force is quite big. It should close quite quickly. So what's going on here is interesting. This is, you see we're getting these infinities. What's going on here is that we've got large errors. All the previous graphs. Okay, so I don't know, at 1.5, is that maybe 15 or something? Yeah. So here, this is not what a damper should do. A damper should do something more like this. It should reduce velocity down to 0. But that other one we're getting infinities. We're getting behavior that was not typical. So with the 15, there's very large errors here. We have to make the step size smaller. And if we do that, now we might have to replot this. That was 0.001, so it's like 10,000 rows. It's taking a little while. You see, we get, now this actually hasn't gone the whole way down. We have to replot. But we are getting the behavior we want. Now that's a very strong lambda, so we'll go back to 1.5. Oh, now the step size is too small. I'm not getting large errors at this thing, so I can make the step size maybe down to 0.05 again. Or maybe 0.01 is a good. We'll make 0.01. So that'll be like, so the other one's 10,000. This is 1,000. This should be quite quick. Yeah, it's quite slow actually. Right. Anyway, vary the mass. So here, this is a light object, and the force is the same. But if you make the object lighter or heavier, it'll take longer to slow down. And go up to 1, it'll take longer. Now, on the next page, they're talking about a specific configuration. So V equal to 0.2, mass equal to 0.1. Lambda equal to 1.5 with H equal to 0.1. So here we're going to get these errors, these oscillations. This is not what a damper does. What's wrong here is we're getting large errors. Problem, you have a light object, because the force proportional to velocity only, it isn't reduced because the object is light. So the object gets lighter, the force stays the same, so the acceleration is big. Large force, large acceleration, and that means the velocity changes a lot. The step size of 0.1 can't be seen with Euler's method. So what we have to do, the velocity changes really quickly, but here it's staying the same. So that looks something like minus 30 meters per second. That's basically not right. What we have to do is reduce the step size, for example, to 0.01, and now these errors will be reduced and we'll get a more accurate picture of what's going on. Okay. The error analysis here, so I'll explain the point of this. Now the table is not well set up. So I wonder if there's any hope I can copy and paste this about it. Oh, I didn't like that. No, it's not letting me do that. Maybe I'll try again. Copy? No. Okay, so what you have to do here, set it up, final time of 1, initial velocity 0.2, check, mass 1.5, lambda equal to 0.5, and the initial h is 1. Okay, so we don't really need this picture here. So this is the first one. So V1 is the first velocity, 0.133. And then Vn is the final velocity, 1.33 as well. These are the exact values. So we got 1.33. It should be 0.14. It should be 0.14. And the local error is the error after one step, the difference between these, which is in the second decimal place, 10 to the minus 2. And then the difference between these is also in the second decimal place, 10 to the minus 2. I'm not sure if you can see my cursor moving here. I'm going between Vn and V1. So then we reduce the step size, it's 0.1, and we go again. So what we see here, this 0.19333, this is our V1, and our Vn is this 0.1424, and then we're looking at the difference between these two. So if you see the 1933, and this is 1934, the difference is in the fourth decimal place. So the local error, the error after the difference between these, the error after one step, is in the fourth decimal place, 10 to the minus 4. And you'll see that the difference between these is in the third decimal place, 10 to the minus 3. And you keep on going down to 0.01 and take this number, so the velocity after one step and the velocity at the end, and compare with the exact values. And what you'll see is that the error over one step, as you make h 10 times smaller, the error over one step, the local error gets 100 times smaller, but the error at the end gets 10 times smaller. So what's happening is, while these errors over one step are 100 times smaller, there are, when you increase h by factor 10, there are 10 more steps. So it's like 100 times smaller, but there's 10 times more, so you kind of get 10 over 100. We'll see this in class. Okay, now looking at these, so this, as I said, writing this program will be the lion's share of the marks in the first assessment, but then there'll be 20% for using your program. So mass equal to 2, lambda equal to 0.2, initial velocity 10, step size 0.05, give an approximate value V10. So set up everything, go down to 10. There you go, there's that 3.67. Let's look at this one, m equal to 2, lambda equal to 0.7, initial velocity 2, step size 0.1. Investigate the behavior of the velocity for large t. So we don't really know, so we're hoping to see some pattern. To see the pattern, we probably should insert the graph. And so the answer here is v goes to 0. Velocity goes to 0. Okay. Next one, mass 0.1, lambda 1.5, initial velocity 2, step size 0.5, final time 1.5, run the thing. This is not what a damper does. What we have here, comment on the approximation, there are large errors. How can the issue in the previous part be addressed? To make the error smaller, reduce the step size. Let's go down to 0.05. The errors are gone. We see the correct behavior. And on the next page, let m equal to 2, lambda equal to 0.2. So, sorry, this thing was smaller h for the, how do you fix the large errors? Initial velocity of 0, step size 0.01, final time of 5, explain the behavior. So what we have here is actually the initial velocity is 0, and it just stays 0. This is a damper, it opposes motion, there's no motion to damper. Okay, so that's that done. Now let's go on to our temperature one. So off we go, let's get cracking. Do I see my code? Okay, so the second one, the Newton one. Okay, my variables. So the most important ones are the time and temperature. I won't be allowed to have a big T and a little t, so I'm going to change one of these maybe to 6. Okay, I also have a heat transfer coefficient. I have a step size. I have a reservoir temperature. And I have a final time. Okay, and my battery is cat, and I need a row counter. It's an integer. What I don't have is initial temperature. That is not a separate variable. The variable is the temperature, and let me put in some values here: 0.05, 0.1, final time 10, initial temperature say 100, reservoir temperature 20. So I have time. I'm going to start at 0. Temperature is equal to cells to this thing. So the initial temperature isn't another variable. Cells to 8. K equal to cells to 5. H is equal to cells to 6. Reservoir temperature is equal to cells to 9. Final time is equal to cells to 7. and or starts with 2. Our loop, so it's like 2 do the stuff. So cells, we want it to be in a row, column 1 to be the time, cells, row column 2 to be the temperature, and then the next time, just put the time up by H. Now, see that's a mistake, it should be time. The next temperature, T is equal to previous plus step size times the slope. You go back into the question and get the slope as the derivative, minus K times temperature minus reservoir temperature. And remember, the other thing to put up is the row number. Or is equal or plus 1, and maybe loop until time is bigger than the final time plus H, something like that. If you're not sure if your program's going to run, do F8 to run through it. See, is it working right? Wasn't working right. Until the temperature is bigger than the final time. That's wrong, that should be time. Oh, my battery is not living. So this looks better. I'm happy enough I'm going to run it. My battery is dying. So I'm going to leave this here and record this and get this up on YouTube. The final one, the shear, if you have any difficulty with it, you send an email or see it in the lab.